Good evening, all. I, Dr. Prabir Kumar Shetty, the convener of this FDP, welcome you all to the second day of third session. That means 2 days it is third session, but in the FDP it is the third session. In this session, our research person is Dr. Sikha OK from University of Pompeu Fabra, Barcelona. So I like to introduce her. Sikha received her BTech degree in Information Technology from Calicut University, Institute of Engineering and Technology, Calicut, and MTech degree in Computational Engineering and Networking from Amrita School of Engineering, Coimbatore. Presently, she holds the position of a senior researcher at the Barcelona MedTech Research Group, University of Pompeu Fabra in Barcelona, Spain. Previously, she worked as a visiting researcher at the Center of Biomedical Engineering Research Group, Polytechnic University, Catalonia, Barcelona, Spain. Before taking on her current role, she worked as an assistant professor in the Department of Computer Science at Amrita School of Computing, Amrita Vishwavidyapit University, India. Her primary research interests include explainable AI, uncertainty in deep learning models, and computer vision applications in agriculture and healthcare. She has authored numerous publications in Tier 1 journal and conferences. So I welcome you, madam, in this session. So I hope all of our participants, that means all these faculties of the different states and different institutes of our country, India, will enjoy your session. Now the session is yours.
Yeah. Thank you. I'll share my screen.
Yes, ma'am. You can share. Yes, it's visible.
Okay. So hope it is visible in the presentation mode. Okay, so thank you for the kind introduction. So myself, Shika, I'm currently working as a senior researcher at the Barcelona Center for New Medical Technologies. So my research group is an interdisciplinary research group, so in which includes both the biomechanical domain as well as AI and computer vision domain researchers. So my position in this research group is mostly towards computer-aided surgery and provide AI solutions for that. And I work closely with doctors from Europe, where we are working on abdominal cancer evolution and building most trustable AI solutions for computer-aided surgery. So thank you again for inviting me for this talk today. So the title of my talk is From Black Box to Glass Box, Building Trust in AI with Explainability and Uncertainty. So I would like to have a discussion on these two aspects of, AI research, that's explainable AI and uncertainty quantification in AI solutions, mostly towards computer vision based applications and medical imaging. This is a brief abstract. Brief abstract of today's talk. So I'll be I'll be talking about AI powered solutions. Sorry, if you all can mute your audio, would be really great. Thank you. AI powered solutions and its pros and cons. And I'll start with the basic definitions of explainable AI. So what is explainable AI? Why is it important? And how we can achieve so-called explaining this AI models or make AI models more transparent for critical applications like national security or healthcare. There, I would like to have a discussion on the current state of the art in this domain and what kind of research that we are doing in our lab in this direction, particularly on post hoc and anti-hoc explainable AI methods for computer vision, and a brief introduction to uncertainty. So in fact, explainable AI and uncertainty go hand in hand. One talks about the confidence of the model, where the other one talks about how uncertain or certain the model is in its predictions. So I assume that you all might have had a detailed overview of deep learning for computer vision in general, or medical imaging in particular. So I'm going to talk in that, from that perspective. So as we all know, from the very basic applications like, say, starting with image classification to the very complex computer vision based problems like visual question answering or generating image descriptions, prognosis, diagnosis, whatnot. Everywhere we have seen these kind of papers and research, research abstracts that comes and says like AI can perform better than a human expert. So the real question comes, should we really trust these models? So as we all know, if any AI-based solution is a deep learning model that that tries to understand or try to derive a complex mathematical function between the input and the output. So it purely depends on what the data that we are going to put into the model to train the network and to make the prediction. So this question was it has become really relevant maybe after this first incident when the Google self-driving car caused its first crash back in 2016. So Google self-driving car is one of the pioneer or one of the most, where all the different types of computer vision or AI solutions comes in picture. So when this incident happened, when people try to decode the reason behind this incident, at the ground level, the reason was an AI model, uh, uh, AI models failed to differentiate between two very similar classes. So that was the very basic reason behind the first crash of Google self-driving car. So from this moment onwards, I think people started questioning the trustworthiness of any AI model, whether they are really reliable or whether we can rely on the numbers. And I don't remember the exact year, but this was another major incident where an MIT researcher, Joy Volankini, come up with some findings of her own regarding the face recognition system. So as we all know, face recognition systems comes in a category where AI can perform better than human beings. But she found that the face recognition system deployed in her institution itself is is failing to differentiate or failing to recognize black women. So that was the first point where she started a legal league against the AI solutions because the AI solutions are highly biased towards the gender and the races. So we had so many other, examples like this where we came to know that we cannot trust these models just based on their numbers. Because so far, to evaluate all of these kind of AI solutions, what we have is some kind of numerical evaluation metrics. Say, for example, if the task is a classification, we used to say the model is say 99.9% accurate or precision, or we have other metrics like precision and recall. But all of these are just like numbers. So it came to a point where researchers understood that we cannot trust any of these AI models in terms of any of these numbers. So that actually motivated towards this particular line of research, which is known as explainable AI. So the reason is so far, whatever we have to evaluate this AI model is just based on a number. But as a human, we need more reasoning behind the prediction. So if we are saying a particular aspect of, say, any particular scenario, we normally come up with some human understandable concepts or human understandable reasoning behind our decision or a prediction. So that is the major aspect of this particular research line, explainable AI. So let's see what is mean by explainable AI, or it has many other, synonyms as well. People used to call it as explainable AI or interpretable AI. But what exactly it is, to be honest, there is no consensus yet because it's still in its infant. It's kind of a very latest research domain. So it purely depends on who is asking for explanation. Say, for example, as a model creator like us, if we are asking for explanation, we will be more interested to understand, or we would like to explain the inner working of the model. So what is the reason behind this particular decision? So when I plug in this particular data, what are all the neurons, or neurons who are, responsible for this particular decision? So for model creators, for us, the explanation is mostly kind of neuron level understanding on what the model is doing, and we can use these kind of understanding to improvise the model. But then, if the person is a model examiner or a regulatory body, for them, the explanation is mostly on how the input and output variables are related to each other. So it's kind of local feature attribution. So I can say, so if I change this part of the input, how the model prediction is going to change. So for them, it is mostly try to understand the bias in the model in terms of the model itself, or in terms of the data it is being used. So for a model examiner or a regulatory body, the explanation is mostly towards the correlation between the input and the output. The next question is why it is so important. The first thing is Google Trends. So this graph is from a recent Google search on this particular term called explainable AI. So the exponential growth itself shows that people who are all doing, especially academic research or industrial research in terms of AI, they want to include some aspect of explainability or interpretability of their model in their publications or the products, primarily because of the regulatory bodies. So in European Union, there are strict rules of GDPR in terms of sharing data, particularly medical data, and also in India also I think there are a lot of rules and regulations that comes to and tries to regulate the AI solutions and the deployment of AI solutions, particularly for very critical domains like national security, as I mentioned earlier, or the healthcare domain. So another reason is this kind of explainability will bring some kind of transparency to the model. It's not just a prediction and accuracy in terms of some numbers. It also provides some reasoning of why the prediction is like that, or why not this is like that. So when we have a misclassification, if we can explain the prediction or the reasoning behind the model's prediction, we can understand where and why and how the model went wrong, which will also facilitate a better model validation and debugging. So I have an example here. So in this particular example, so assume that there is a classifier, and the classifier classifies husky, which is being misclassified as wolf. So earlier, what we used to do is to print a confusion matrix that say this many instances of husky is being misclassified as wolf. That's it. But we never knew what was the reason why the model was not able to do the classification correctly. So here comes the explanation map for the same task. So when you see the explanation map, now we know that the model, misclassified a husky as a wolf because the model was not looking at the region of interest, that is the face of the object. Rather, it was looking towards the background. So when we know this is the reason behind it, what we can do, we can retrain the model, adding more instances from the same class of different background, and make sure that we get enough variance of data within the class for the model so that the model can perform better and it can reduce misclassification over the time. Another reason could be we can use this kind of explanations to understand the weakness of the model, especially bias in terms of data. Say, for example, I have given two different examples. In the first row, we can see that even though the model make the right decision. So the input image is of a nurse and the prediction is a nurse, but then in this case, the model is looking towards, some generic aspects, say some features from the background, but not very specific. So there the model could be a biased model, but in the unbiased example, when you see to understand a nurse or a doctor, it is looking at the stethoscope. So for a human, for a nurse or a doctor, stethoscope is a very, generic concept that we use to understand who the person is. So these kind of, explanations primarily will help us to understand the model and also to improvise the model by debugging the fault within the model or within the data. So the next question. So now we answered what is meant by explainable AI and why it is very important. Now the third question, which is very important, that how to explain a model. So for that, maybe I should start with something called intrinsically interpretable models. So intrinsically interpretable models are very simple machine learning or classical machine learning or deep learning based models. An example is a decision tree. So which the reason behind the prediction of the model is interpretable just by looking at the model's parameter or the model summary. Say, for example, in this case of decision tree, it's very easy for us to understand the reason behind any decision. Say, for example, the reason behind this decision, we can just traverse through the branches starting from the root to the leaf node. It's very easy for us to say we can easily generate a conditional structure. So age less than 25, and if it is a student, then the decision is yes. So it's very easy for us to understand or derive some kind of human understandable concepts from these kind of models. And in this case, say it's a linear regression. So we can say that age is very important. And then the most important parameter is income. So these are all the intrinsically interpretable models, which are very simple mathematical functions, try to map input and output. And then from their structure itself, it's very easy for a layman person itself to, or himself or herself to understand the reason behind their prediction. But the problem is that, so these kind of very intrinsically interpretable and simple models, we can use them to solve small tasks, very easy tasks. But if we want to solve complex computer vision tasks, as we discussed before, we cannot rely on these kind of intrinsically interpretable simple models. Obviously, we have to move towards complex models. So I have a graph here. So when you move from the left to the right, so these models in the left region, they are very interpretable and very easy to implement, easy to understand, but they are not suitable for complex computer vision tasks. And as we move from left to the right, the model becomes very complex. They become very less interpretable or explainable, but they can solve complex, computer vision problems. Say, for example, decision trees, you can just traverse through from the root to the node, and then you can understand the relations or the reason behind the prediction. So if it is a linear regression, you can change the decision boundary patterns, and then you can understand if I change this parameter, how it is going to be, how the regressor going to behave. And I think the moment when we switch from decision trees to random forest, a kind of black box model, black box nature is getting inherited from this model. So for example, when it comes to a random forest, and if you want to understand the why random forest gave this particular prediction, we may have to decode multiple decision trees, and then we may have to come to a common ground. Okay, because of all these reasons, this prediction has been made. So from random forest onwards, I feel the black box nature starts. So as we move from random forest to neural network, so this is a very simple multi-layer perceptron, which is highly densely connected between the layers. Because of the number of parameters, it is very less interpretable. And when we move from one dimensional to 2D or 3D, where we primarily use a very specific network architecture called convolutional neural network. So there, the number of parameters may be millions or billions, make it even more less interpretable. So the question is how to explain these kind of architecture. So now our focus is mostly towards architectures that comes to this part of the talk, that is convolutional neural network. So how to explain these kind of complex computer vision based models, say convolution neural network, autoencoders, etc. So in the literature, based on the literature, the explainable AI methods that are available out there can be broadly classified into two different classes. One is post hoc explainable methods. The second one is anti hoc explainable methods. So post hoc explainable methods, the idea is the model is already trained. So these methods try to analyze and interpret the reason behind the model's prediction after it has made prediction. So the model is trained and deployed. After that, we are trying to use some mathematical formulations or DL-based solutions that will come later to understand what is the reason behind it. And the mostly available solutions are in terms of heat maps. So heat maps just say, based on the heat, wherever you have, say, this red region, that are the regions where the model has considered the most to make that particular decision. So that is post hoc explainable models or methods, wherein anti hoc explainable models or methods are the most optimized way of doing that. So whenever you design a model, within the model design itself, you should have a module to explain its own prediction. So it's something like you have a model which is which can do a particular task, say classification, along with doing the task, say classifying images or videos or whatever data you have, along with the task in hand, generate the explanations also. So something like, say, decision tree. So these are the three different types of methods. Black box model, we don't know the explanation. So the conclusion is we cannot trust them. Post hoc methods, the model is already trained. We are trying to decode or understand the already trained models. Anti hoc explainable models, within the model development itself, whenever you develop a model, you introduce a module for explaining the model. So the model will be doing the task. Also, it will generate its own explanations. So let's see the existing literature in this. I am just you know uh, providing literature on post hoc methods, because when you see the explainable AI state of the art, more than 95 to 96% of the research out there is mostly based on this particular aspect, that is post hoc methods. So post hoc methods itself, so there are different way of classifying them. So I just put the one that I felt it's more relevant. So there are many methods which are purely based on gradients. So it's based on how the gradients flow from input layer to the output layer and output to the back. So it starts with class activation maps, saliency maps. GradCam is one of the very famous one, and there are different versions of GradCam out there. So all of these kind of methods try to understand or generate heat maps, and based on the heat map, they try to explain the reason behind prediction. So these gradient-based methods, mostly they are applicable only for architectures like convolutional neural network, which means most of them are not model agnostic, they are model specific in nature. So the next category is model agnostic methods. So it's the two famous candidates in this category. They are Lime and Sharp. So these two kind of models can be applied irrespective of the model. So you can also use it if your data is text. You can also use it if your data is image, video, or whatever it is. And another category is deep learning based explainer. So there are a lot of research happening in this research in this particular domain of post-hoc explainability, where people are coming up with a deep learning model which can explain another deep learning model. So in this kind of solution, what I've seen is, an extra effort has to put to explain the explainer, because the explainer itself here is a deep learning model that try to explain other deep learning models. So we need some kind of interpretation or explanation of the explainer itself. We will have a discussion on this. And the fourth category is one of my favorite category. So that's empirical analysis or meta-analysis. So here the idea is, if we can use our high school math to decode and understand this complex architectures, deep learning architectures that say convolutional neural network, that is the best thing to do, right? So this kind of analysis, they are more theoretical in nature, but they use very simple concepts like, say, singular value decomposition or very simple matrix decomposition methods to understand and decode the reasoning behind the prediction of these complex models. So let's move towards my ongoing research in these categories. So let me first start with what we have done in the post hoc explainable methods in general, and also we have some use cases for medical domain. So and then we will move towards few. I think one of my work on Andy Hock explanation models, and then science-induced deep learning solution. So it's this is a new area we just started our study on, where we are trying to distill a black box into interpretable expert. And for individual expert, if we can induce the actual physics, or say for example in the case of medical domain, if we can induce the what to say, the experience and the knowledge of a doctor as a medical report, how it is going to be, and the data driven methodology to understand the actual reasoning behind these models in a using very simple mathematical formulations and uncertainty in deep learning. So let me start with the first aspect of what our the very recent research, where we used it comes under empirical analysis that I explained earlier. So here we have used a concept called dynamic mode decomposition, which is a very simple matrix decomposition. I'll explain this in detail. But let me first explain what is the motivation behind this particular work. So as we are all working in academia, most of us, and industry, reproducibility of a research is something that we really want these days, isn't it? So we are very much used, or most of the time to start a research, maybe because of less resources that we have, we are forced to use pre-trained models that is being reported in any of the published research. But when we use these pre-trained models, we may or may not, mostly when it comes to medical domain, we may not have access to complete test or train data, or we don't know the very particular parameter details of the model, say loss function or any other parameters. But still, it's come to a point where we have to trust the authors and use the model and the weights, whatever they have given in their website, publish in their website, or sometimes we may have to mail them and ask them. So whatever they are going to give us, we are going to use that to advance our research. So the question is how to trust them. In general, the traditional matrices to evaluate any model, say accuracy for classification, die score or IOU for segmentation task. So whatever be the task in hand, it demands for train and test data. But if we don't have access to train and test data, is there a way to assess them? Obviously, we cannot assess them in a very specific way, but at least is there a method to evaluate the quality of the model? I mean, whether they are uh, properly trained, is it undertrained, is it overtrained, or whether what is the generalization aspect of that? So at least to deal with this aspect, the quality of those models, if we have simple tools, say some very simple mathematical tools to understand the evolution and effectiveness of these kind of models would be really nice. So that is the motivation behind this particular research. So dynamic mode decomposition, it is a matrix decomposition method, which is primarily being introduced in the fluid dynamics community to model any system without an equation. So it's a completely data-driven approach. So it's kind of mostly for fluid dynamics, the actual flow is you have a system of equations and then you model the system. But in that case, we may not be able to actually understand the other environmental, factors that may affect the system. So that is the motivation behind this particular theory. So here the idea is go back. So you have a data, that's the observation that comes from the system. Using those data, can you model the system back? So that is the basic theory behind this particular decomposition method. And the cost of DMD is the cost of singular value decomposition, because the dynamic mode decomposition built on top of singular value decomposition. So as per the theory, if you have to apply a dynamic mode decomposition, we need say observations from different times. So in our research, what we have done is, so this is a post hoc method. So the CNN is already trained for a particular task. So we evaluated this empirical analysis on 2 different tasks to show that this method is task agnostic. So if you have a CNN backbone, say whether it is a segmentation, classification, or any other task that you do, if you have a CNN backbone, you can use this analysis to at least understand where the model stands. Okay, so for that, the first objective was to give a linear representation. So we didn't consider in this research, we considered CNN as a linear dynamical system. We didn't consider the nonlinearity aspect because we need more mathematical formulations to deal with the nonlinearity aspect. And as we know, the CNNs, every filter learned from the previous filter. So the learning happens incrementally. So we extracted the feature map from individual filters and we consider them as they evolve from one filter to another filter. So the evolution is kind of what is the information or what is a pattern that is being learned by these filters one after another. So that's going to be the snapshot matrix here to apply DMD. So dynamic mode decomposition will decompose the snapshot matrix and then into DMD modes and eigenvectors. And from these eigenvalues, we have this DMD CNN analyzer. So this DMD CNN analyzer introduces few customized matrices like entropy of DMD mode, spectral gap, and DMD modes with 0 amplitude to understand the evolution or the learning reason behind these models. So the first observation what we found was, as we learned any CNN or any deep learning model over epochs, so the system, since it was being considered as a linear dynamical system, so the system starts from a very random distribution and then it tries to converge over epochs. And then we introduced a few matrices. The detailed aspect of all of these study and analysis is available in our paper. So in our experiments, we found that this particular metric, that is entropy of DMD eigen spectrum, they had a correlation with the accuracy of the model. So what we found was the entropy of this DMD spectrum is, if the entropy is less, the model is more accurate. So the idea is very simple. As the model goes through the epoch as the model becomes more generalizable or stable, the entropy, that is a measure of randomness, is getting reduced. So that's a very basic understanding of the whole concept. So we analyzed the application of EDMD, that's what the metrics called, in terms of classification and segmentation across generic image classification data sets and also medical data sets. And we tried whether we can use this particular metric to understand whether a model is poorly trained or well trained model. Because if we don't have access to full train or test data, it is highly impossible to tell what exactly the test accuracy is. Okay, so instead, we can use these kind of, say, this particular metric to understand, or at least to try to differentiate between poorly trained model and well-trained model. We also tried just by taking the stable DMD modes to give an interpretation of the decision. So again, these interpretations we have generated heat maps. So the heat maps, these are all the heat maps that have been generated by this simple method. So this heat maps will highlight the regions that is being considered by the model to make the decision. So the heat maps are highly localized, and they are highly, it is just looking at a very specific part of the image to make the decision. So moving towards the next category of interpreters, that is deep learning based explainer. So the previous one is the empirical based explainer. So where we used a very simple matrix decomposition method to explain the architectures. So in this research, we introduced a deep learning based explainer. So as I explained earlier, the explainer itself is a deep learning model. So we also have an explanation for the explainer. So here we used a conditional GAN to understand the reason behind CNN prediction. So this particular model also, they're task agnostic and model agnostic in nature. So wherever you have a CNN backbone, you can use this particular model. So the idea is conditional GAN work on generating, they'll generate images, but we can condition the GAN. So to condition the first part of this network, we used the cumulative GradCam averages. So cumulative GradCam averages are generated by the intermediate filters from the underlying convolutional neural network that we are trying to explain. And these CGMAs these CGMAs are used to condition the network. So we tried two different types of conditioning the GAN. One is the local conditioning. So as I shown here, local conditioning is after every convolutional block, we have a condition network, and every GradCam from the intermediate blocks are being conditioned and given to the GAN. And the second category is global conditioning. So we call it as GSFT GAN. So in this, all the CGMAs put together pass through the condition network only once, and then pass to the GAN for training. So when you see for the discriminator, the label is the actual GradCam. But in the experiment, what we found was, even though we used the actual GradCam to condition the GAN and to train it in a supervised manner, the explanations that is being generated by our model, so the last two columns, GSFT and LSFT, so the explanations were also have some similarities from other explanation models as well. So which means the model was able to capture generate explanations where GradCam failed, but those kind of regions were very visible from other state-of-the-art methods. And this is few examples from image descriptions. So in that case, say for example, when it comes to image description models, you have two different aspects. So you have a computer vision pipeline and you have a natural language pipeline. So it's a kind of mixing NLP with computer vision. So we also tested the efficiency of this explainer in this realm, and we also have some quantitative measures. So the question, as I explained, the first question is, since it is a deep learning model that is trying to explain another deep learning model, so it's a kind of egg chicken problem. So we have to explain the explainer. So for explaining the explainer, we used a concept, concept similar to LRP, where layer-wise relevant propagation, which is a very famous explainable explanation methods available in the literature. So we try to understand the contribution of individual CGMAs, because the main aspect of our research is CGMAs and how we condition the GAN. So we try to understand the importance of these individual CGMAs by blacking out the individual CGMAs by testing the model. And what we found was for a CNN to make decision, every layer matters, because most of the existing post-hoc methods like GradCams and the different variants of GradCams, they just use a final convolution block. But in this research, we found that all the layers starting from the beginning to the last, from the very first layer to the deepest layer, every layer, in fact, has an importance to understand the actual working of the model. If we just consider the final convolution block, there will be some kind of information loss that we can expect. So moving towards, so these two are post hoc examples of the, the model is already trained and how can we decode. But the very optimal way of designing any AI-based solution is go anti-hoc. Like while you design a network itself, be it a classification task or a segmentation task, whatever be the task in hand. So while designing your network itself, if you can have a capsule or a module which can generate its own explanations on the go while training itself, is very much appreciated, because that will help us to generate more robust outputs. So this is our first work in this direction. So this is the underlying network to be explained. So for any underlying network, there will be a task specific loss. So the task could be so there will be a task specific loss. So if your task is classification, you can have classification based losses. If your task is a segmentation based specific losses, say IOU or dice code, whatever it is. So for any task, there is a task specific loss. And then this is our interpretation module. We call this module as a weight network. So the idea is, whatever be the architecture that you have, whatever be the task that you're doing, you can plug in this module on top of it. It's a kind of an extra plugin. So take this module and plug in on top of your underlying network. So this capsule will generate explanations based on the task. Okay. So now let's see what is the weight network is. The weight network is a very simple autoencoder. So this autoencoder, the output to the autoencoder are the features that comes from these convolution blocks. So we didn't use any other explanation map. It is purely based on the features that is being generated by the underlying model. So we extract the features. So the number of features is eta in our architecture, which is a hyperparameter. You can decide how many feature maps that you want to consider. But my genuine suggestion is to consider all the feature maps starting from the first layer to the last layer, okay, for a better explanation. So these feature maps are passing through this weight network. Now, what the weight network will learn? So this weight network will generate some weighted combination of these feature maps and come up with an interpretation map. So how the weights are being learned, I'll explain that. So this interpretation map is being multiplied. It's element-wise Hadamard multiplication with the input image, which is again fed into the same network. Okay, so this is the architecture, but let's see how the training was. So the training is a two-phase training. So it's a kind of train, pause, and then train again. Train, pause, and train again. Because the input for the explainer module, it should come as feature map from the underlying network. So the minimum number of iteration that the underlying network has to train is one to start this network or to initiate this network. So we train this network first and then extract the feature maps that will go into the weight network. So we have a output that comes after this Hadamard product, which will pass through the same network. So the idea is we are going to penalize. We have an interpretation loss here, so we are going to penalize this explanation module so that it will not or it should not generate the whole image as the explanation, because I'm not looking for the same image as the explanation. I'm looking for the particular position, the most important position that is being considered by the underlying network to make the prediction. Okay, so that is being calculated. This interpretation loss is being calculated based on the prediction of y first, that is a task specific prediction. Y second is the prediction that comes from this input. Okay, where your interpretation map is being multiplied with the input and then go through that. So we are just penalizing the network, focus only on the important part, not the whole images. So the advantage of this particular architecture, what we proposed was, earlier in the literature, most of the explanation modules, they were producing some kind of heat maps. So heat maps requires another manual intervention, like an expert intervention. It's like a AI expert to explain, okay, why and what is being considered. But in this particular Andy Hock framework, we were able to generate concepts, not heat maps, so which does not require another human intervention to understand the reasoning behind it. Say, for example, for cat, for the particular class cat, the cat eyes are important, or what part of the, and we found that different concepts are being learned by the classifier to understand a particular class. So it's not like when it comes to cat, only the eyes. It is also considering, say, the other ear part of the eyes. So we also found that different concepts are being learned by the same classifier to understand the same class. So this was our first entry to the very famous CVPR conference in 2023. So moving on, so I've discussed one sample from Andy Hock, few samples from post-hoc methodology. Now let's see, apart from these kind of techniques, is there anything that we can do? So we have a lot of explanation methods that are available out there. Can we use these explanation methods to understand the trustworthiness? So the answer is yes. So next comes the question, do we need an entire image? Say, assume that you are a doctor. Do we need the whole image to predict the class? So this is mostly what a CT scan machine generates. But for a doctor to understand or to diagnose this, he may be interested only a particular part of the image, maybe this part of the image. So even though we have a big whole, high resolution image volume, CT or MRI volume available with us, for a doctor or for a domain expert, only a part of the whole image is important to make a decision. So the rest part of the image is going to behave as a noise for the model that we are going to build. So if we can just identify the region of interest and then use these region of interest to train the model, that is going to improvise the performance of the model, because we are not giving any noise signals as an input into the model. So that is the motivation behind this particular work. So it's a 3-tier architecture. So what we have done is we utilize the existing explanation methods that are available out there, and we build on top of that. So as I told, it's a 3-tier architecture. We tried initially this for skin cancer classification. So there is a global branch which acts as a as the first, maybe I can call it as a teacher, and there is an attention module, which in where we use the GradCam or any explainable methods that are out there as a hard attention module, and then there is a local branch. So the idea is the global branch is trained for minimum number of epochs, just to make sure that it has already learned some patterns between the input and the output. And based on the global branch, we generated a few explanation maps. So this is kind of what is the knowledge being learned by the global teacher model. Okay. So that is being encoded here. And we use this encoded information to train our less complex local branch or a student branch, I can say. But for the student branch, we are not going to input the whole image. We are just going to distill the knowledge that is being learned by the global branch. So in a way, we are trying to reduce the noisy signals, that is any region which is not important for a model to do the task. We are going to remove them based on post-hoc interpretability modules as an attention module, and we are going to give them as an input into the local branch. So our observations showed that in terms of classical measures like accuracy, precision, recall, F1 and AUC score, we were getting very good performance across different architectures that are available in the literature. And we also noted that since we are avoiding the noisy part of the image, anything other than the region of interest is the noise, the networks were able to, converge very easily. Like with less number of epochs, it was able to converge. So this is where I want to show, like in this line of research, you can also think about things where you can use use the existing research and build models, more trustworthy models on top of that. And few other research is this first one is the rule-based explanation of deep classification networks using regional feature. So in short, here we try to combine these two realms together. One is the machine learning community and the deep learning community. So we try to explain the convolution neural networks using very simple decision trees. I'm not going to explain this. All of these are available in my profile. So the most important question, all good? Is there anything to worry about? So I think to explain this, I feel like this very famous book, The Inmates Are Running the Asylum from Alan Cooper, is really relevant here. So in this book, he talk about, even though we have good softwares, they're talking about why the user interfaces are so bad. So the same thing is happening with explainable AI line of research also, because definition, objectives, what, why, and how explainable AI work, everything is driven only by AI researchers, often without sufficient inputs from, say, domain experts, say doctors. Another one is there are no benchmark matrices available. There are few matrices available, which is purely based on the robustness of the model. But most of the matrices to evaluate the existing explainable AI methods are purely based on, visual evaluation that is highly subjective. Maybe just by looking at a heat map, I can say this part of the image is very important. Somebody else can say, no, the other part is so important. That is highly subjective. So we don't have a particular benchmark matrices to evaluate these XAI methods. And we also need, more methods that are anti-hoc in nature, and also they can generate some human understandable concepts. And I think this is very important, lack of domain-specific workflow. Say, for example, for a doctor, he may be following some rule book to make, say, some diagnosis or a decision. So in this case, that particular workflow is very important. But fortunately, in this domain, a lot of research is being happening, called mechanistic interpretability. So they are trying to decompose the black box into a mixture of experts, and each expert is being trained only to follow a particular rule of, say, the actual workflow as a human expert, and over reliance on positive explanation. So all of these drawbacks actually says that this particular research domain has a lot to do. So a lot of research opportunities are available, and this line of research is very important because of, because of AI regularization across the world, different countries, different forums. So this is an open book for anybody who wants to, start their research career. So moving towards the second part of answer the talk, I won't take much time in this. So that is uncertainty in deep learning. So the very basic idea is, see, so far all of the deep learning solutions that are available out there. Let me take classification as the example because it's very easy to explain it. So if you have a trained classifier to classify cat versus dogs, whatever be the input that you are going to give, okay, the model is trained to say either class 0 or class 1. Assume that the probability distribution from the finite layer for class 0, say 0.7 and 0.3, okay? So in that case, I would say the clear distinction is that particular image or input goes to class 0. But what if the distribution is 0.55 and say 0.45? So there is no much difference. So as a human, if I am not so sure about any prediction, I will say I don't know. I need some expert opinion. Unfortunately, the existing deep learning solutions, they don't have the freedom of saying, I don't know. I need an expert opinion. So that is where the concept of uncertainty comes in. So the uncertainty methods, they try to quantify when the models, when can we trust the model's prediction. It has a lot of, applications in healthcare. So it is mostly like we are trying to train a model, and then we are trying to understand how confident or certain the model is in its prediction. If it is not so confident, we are going to flag the human expert. That's going to be a doctor or a physician. So this is one of the pipeline that we developed in our lab in association with the oncology department of hospitals in Barcelona, because they wanted a human flagging system. This task is for image segmentation, lesion segmentation, especially for abdominal cancer analysis. We have worked on the liver cancer evolution, so on CT volumes. But this prototype, whatever I've shown here, is illustrated using skin lesion analysis. The pipeline has 5 different components. So it's a kind of benchmark to see the quality. So when it comes to medical domain, one of the major difficulty is with the ground truth. It is very difficult to get a ground truth, especially for, say, segmentation task, which is very important for the localization of a lesion. So this particular study tries to understand whether we can avoid lesion at least during the test time. So if we can use the uncertainty aspect of the underlying model, using those uncertainty maps, because uncertainty maps are going to tell you where the model is confident and where the model is not confident. So to the ground level, it is something like where the model is very much similar to the ground truth, where the model is not so similar to the ground truth. But it's a kind of distribution analysis. So we tried on the test time, if we can avoid the use of ground truth, would be really nice. So for that, we used uncertainty measures. So we have a segmentation model, which is static. So we trained it only for once for the whole study. And the second module is the uncertainty quantification module. So there are a lot of methods available in the literature. Few of them are Monte Carlo dropout. So the idea is, we all know we can use dropout during training to make the model, generic, more generalized, like not overfitted. So in this idea, we can apply a percentage of dropout, which will switch on and switch off the neurons randomly during training. But Monte Carlo dropout is applying dropout during test time. So what will happen is, if you pass an image through the network and if you apply dropout during the test line and you repeat the testing for say 10 times, from a single deterministic result, we are going to generate 10 different results. So it's primarily the idea of uncertainty quantification module. We call them as UMs, is to convert a deterministic prediction to a distribution so that we can apply this probability measures on that. Another method is TTA, test time augmentation. Again, we know what is data augmentation during training, but test time augmentation is we apply augmentation during testing. So again, the idea is from a deterministic output, convert that into a distribution and then normal assembly. So after this uncertainty quantification module, we can estimate uncertainty using different aspects like confidence map, entropy or mutual information or KL divergence. That's going to give us, uncertainty maps like this. So in this case, if you have a red region, the meaning is the model is highly uncertain. It is not so sure whether that pixel belongs to a foreground, that is a lesion, or a background. So we used in our, this is the first part of the module. And then we introduced, a multi-branch regressor. So this regressor is going to take the input image, the predicted segmentation map from the deep learning model. So again, this is one-time training. So it's not that much complex to train one segmentation model once. So after that, it's only what we need is a predicted segmentation mask. And we are also using these uncertainty maps. So as you see, when you test an image, so this regressor is going to generate the segmentation quality. Okay, so in this experiment, we used dice. If you want AUC or any other matrices, you can replace that. So when you see during test time, you don't need the ground truth because this is one time, the segmentation model is one time trained, which is static, keep aside. And the rest of the thing you can just do only by using the predicted segmentation mask and the uncertainty mask. So the cost of generating uncertainty map is very less compared to generating ground truth, which need a lot of manual, intervention. And we also experimented on this aggregate uncertainty score because we have different uncertainty estimates. And because we want to know rather than just giving this kind of heat maps, if I can give one particular value between 0 to 1. So if the value is more towards 1, the model is very uncertain with respect to that particular case. If the value is towards 0, the model is kind of is confident in that case. So we can just filter out these outputs based on the uncertainty aggregate score. And then we can use these outcomes to flag the doctors or sonographers to redo the scan or reanalyze the whole CT volume. And in this particular work, we tried can we use any other lesion-specific features to reduce the uncertainty of a model or improvise the confidence within a model with respect to segmentation as a task. So the idea is this is a UNet architecture, which is a well-known architecture for medical image segmentation. So in this architecture, the generic UNet architecture takes input and the ground truth and generate the segmentation map. So what we tried was the lesion specific, though any features that explains the lesion. So what is the area of the lesion or the boundary details of the lesion. So this is a kind of the initial pilot study we used a structured data. But if we have access to a medical report that actually comes from the doctors, you can replace that also here. So this data that is very specific to the lesion is being combined with the bottleneck is the latent space of the unit. So in the encoder learned from the image, in the latent space, we also combined this lesion specific features so that we want to learn the whole model from the very specific lesion details as well, but the task is segmentation. And we analyze the whole model's uncertainty in terms of uncertainty modeling. I explained earlier, Monte Carlo dropout, uh, test time augmentation and assembling of with different combination of uncertainty estimates like confidence map, mutual information, entropy. And what we found was the proposed model, we call it as meta unit. The uncertainty was very less, which means the model was, you know, more confident because it is also getting an extra information and additional information, which is very specific to, lesions. So that's all for today. Now I am open for questions.
Ma'am, hello, good evening. This is Saili
Yeah.
Salkade from Mumbai, and I'm doing my research in the TB detection uh, and using the deep learning and explainable AI techniques. So, is there any? Can you guide me regarding some of the key points from research point? Means how I can these models they grad cam plus plus or score cam, yeah, line and all these models are existing. So
Yeah.
if I want to do some research work, real research work in this explainable AI, so what points means what things can I do regarding that?
Okay, so let me clarify one thing. So are you trying to develop a new explainable method or what you're looking for as a part of your research? Because I explained a few methods like that we developed our own explainable XAI algorithms or models, which which is motivated from methods like what to say GradCam or GradCam plus plus. So in your research, are you going to decode your model and understand what is going to happen? Or do you really want to develop a new explainable AI method? So you can actually go in these two directions, but coming up with a, self-explainable method may take some time. That's what my personal experience. But if you are using the existing methods and coming up with some hybrid methods and then using that to improvise your model or to make your model more robust, that will be, I mean, easy to go.
Ma'am, actually, what I have done is I have applied all these techniques, GradCam plus plus, then ScoreCam, Line, and I tried to see the results. So for
Mhm.
ScoreCam, I could get the some proper heat map, and GradCam and all these things. The heat map means the sometimes what happen. It is basically chest X-ray, so it is not showing the proper regions, location of the disease. The heat
Mhm.
map is going somewhere else, means it is delocalizing or it is not capturing that region properly.
Okay.
So this was the observation while using different techniques, and
Okay.
I tried to use the Shapely also and
Mhm.
find out which features were contributing towards my research. Means for the TB detection, like age, weight, you can say, or the drugs which were used. So, in that direction, can you guide if I have the existing techniques with me, and how can I improvise them or use them from research point?
Yeah, if you have, I mean, if you tried all of these existing techniques, so this is what I was explaining. These methods are purely subjective. It may be different from task to task and data set to data set. So my suggestion would be if you have access to any clinical data, say for example for patient specific clinical data, you can combine that clinical data along with this explanation methods, whatever you tried, which will help these explanation models to go more localized and give you more relevant explanations, I would say. So at least that's what we observed in our research.
Okay, so that meta unit model you just now you showed, that can be
Yeah,
used in my case. You can
yeah,
provide some help regarding that
yeah, yeah,
model.
yeah. Yeah, yeah, yeah. I think the meta model, whatever I explained, is we tried it on uncertainty, but the same method, the same idea can be you can use it in explainable AI methods also. The paper, I think it's online in my profile, and if you need any help, I'm happy to help you there.
Okay, I will mail you personally, ma'am, whatever is my requirement according to
Sure,
that.
sure, sure,
Yeah,
sure.
thank you so much. Very nice session, ma'am. Really enjoyed.
Thank you.
Madam, this is Shivadasan from Vidya Engineering College, Thrissur, Kerala.
Okay.
Yeah, I also
Okay.
did my MTech from Amartya Vishwavidyapitham from the
Oh,
same
nice.
SEN.
Okay, okay.
Ah, ah,
I,
ah.
I am basically from Kerala.
Oh, I see. Actually, I could not get your email ID. Something was shown, but I could not note down. So, could you please give me that email ID once again?
I think I can put it in the chat.
Okay, that will be great. And in which
Yeah.
year you did there, MTech?
I did from 10, I think to 2013 pass out.
Oh, I see. Okay. Thank you.
Yeah, I put it in the chat.
Any other queries, please?
Actually, ma'am, one more question came to my mind that is there any upcoming explainable AI technique, because this has been used for a longer period, right? Means grad
Uh,
can know this. So is it
yeah,
uh,
yeah.
something?
There are a lot of other variants of I mean, grad cam. People call it like score cam. I mean, so many different variants, I would say. But if you ask me what is the latest version of cam or grad cam, I don't know. Maybe Google
Okay.
Scholar will help.
So it might vary, no, according to the type of data or like that. And some might give some technique might give work better for that data set or some like that. It will change
Yeah,
from
yeah,
data to data.
it will change, but I would say to come up with a, if you are observing, I mean, if the change is too much, I would suggest to come up with the hybrid approach so that you will have the, advantage of all the methods, I would say.
Okay, ma'am. I have tried something regarding multimodal AI also, ma'am. So what I took
Okay.
is the gene export and this chest X-ray information, and I fused
Mm-hmm.
together. But as
Okay.
compared to the chest X-ray or images, it was the results improved tremendously when I fused both of them, textual and image data. So
Okay.
that part, that output, I can use as your meta unit, like just you now showed me, no, in the same format.
Yeah, yeah. In the meta unit architecture, because that was a pilot study that we did in our lab. So the metadata of the lesion was structured in nature. So to convert that into the shape of the latent vector of the unit, we just used a simple embedding layer. But if you have access to, say, medical report, you can replace that with any kind of maybe any language based models or embeddings which can extract more patterns out of the medical data, and you can provide them, or any Gen AI methods can also be used, because I've seen few papers where people use this kind of medical report and then convert that into a low dimensional representation and then use that further to improvise any other architecture or any other task. I think that would be a good idea to explore.
Okay, ma'am. Thank you so much. I will just mail you, and please share me the paper or some help if I require regarding that.
Sure, sure, sure. Whatever
Okay,
I
ma'am.
can.
Thank you once again.
Abhishek,
Respected Dr. Sikha, on
Hello.
behalf of the organizing, respected Dr. Sikha, on behalf of the organizing committee, I extend my heartfelt gratitude to you for delivering such an insightful and enriching session today. Your expertise and expandable AI, uncertainty in deep learning, and computer vision application has truly burdened our perspective and provided valuable knowledge to all of us. Once again, thank you, Dr. Sikha, for sharing your expertise with us.
Okay. Thank you. Thank you for inviting
Thank you.
me. I hope I was, I was able to explain few things, whatever I'm doing here. So thanks once again.
Thank you.
Thank you. So, Dr. Sabira, I can leave right now, right?
Yes, 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 for sure.
Thank you. Thank you.